So I'm getting to the last topic. And this topic is the adding covariates in the DSEM framework, and we're going to also discuss the new residual DSEM model. So we start with, we're going to use the mere-1 model as it allows us to kind of more fully explore this issue about how to add the covariates in the DSEM framework. So we are going to, but similar arguments apply also to the AR1 model, but it's a little easier to work with the mere-1 model. So there's 3 separate models, actually. There's 3 different ways you can add a covariate in this framework. So here is what we call the residual AR model. And again, without this thing, that was basically just a mere-1 model. So you have a factor, you have the observed variable measuring a factor, and then the factor has an autoregressive equation, which is the mere-1 model. Now we are adding a covariate in the first equation, so which is basically we are adding the covariate outside of the autoregressive process. You can also do this, we call this second model, which is called the full AR model. We can actually add the covariate in the autoregressive portion of the model. So you can see it's in the second equation, or you can do both. You can actually do what we call the joint effect model. You can add the covariate, the same covariate here and here. You know, it's another, again, you know, example of how the standard SEM logic does not apply to the DSEM modeling framework. Of course, this is not possible to do in standard SEM models. You know, I mean, you have just one indicator here. You cannot identify both 2 regression coefficients if you just have one variable. It's just one, but you know, okay. So the reason actually the reason this logic actually the SEM logic fails here is because you know the SEM logic is based on sample mean and variances. This does not apply in time series models because you know sample mean and variance are not sufficient statistics, and so they don't explain. There's a lot more to the model than sample mean and variances. Okay, so these are the 3 models, and just to understand a little bit about how they differ, we're going to consider the implications for the expected value of the dependent variable given the covariate. In the residual AR model, the expression is very simple. And so here's the expression. So the mean of this process is 0. So the expected value of y given the x is just the standard. The expected value of this is 0 and this is 0. And you can just get mu plus beta xt. So it's very simple. And that's kind of the appeal of this residual AR1 model. So this conditional expectation resembles much more the standard regression model. So it's very easy to interpret. But what you can notice here is that the value, the conditional expectation, is affected only by the covariate at the current period. It's only affected by the covariate at the current period. And that does not happen for the full AR1 model. So you have sort of an accumulation effect of these covariates. So the conditional expectation of the dependent variable given the covariate is this infinite sum here, and it shows that not just the covariate at the current period affects your value, but also from the previous period. So whatever happened in the previous period also affects your the expected value of this period, and so on. So because this is the autoregressive parameter to this power, this actually converges to 0. The autoregressive parameter is smaller than 1, and so this has a diminishing effect. The covariate values from the previous periods have a diminishing effect on the current period. However, again, this is an accumulated effect. So whatever happens in the previous periods can have an effect on the dependent variable at this current period. And finally, the joint effect model has both of these. So it has the direct effect, and it also has this accumulated effect. So this is the general picture. However, you know, we kind of got, you know, as we kind of worked our way through this modeling, actually, we started first considering this very simple case of when the covariate is actually the time, which is basically the linear growth model. And Ellen has a paper on that, which we really like, and that shows that the residual AR1 model and the full AR1 model are actually equivalent to each other. And when they're equivalent, that means that the two reparameterization of each other, and you cannot, one regression effect is equivalent to the other regression effect, and therefore you cannot identify both of these effects at the same time, which makes the joint model not identified. So let's just dig in here. So the residual AR1 model, the linear growth AR1 model, basically, it can be expressed like this. So you've got the linear trend over here, and then you have the residual, and you have an autoregressive equation for the residual. So I switch back to this to the AR1 framework here for a minute. So the full AR1 model. So again, the trend here is actually outside of the autoregressive equation. Now the full AR1 model, the trend is within the autoregressive equation. And note here that the effect of time here is direct. You have just this coefficient. That's how the time affects yt. But here, it's not just this, but t is actually inside yt minus 1 as well because of this equation. So the effect of time is a little more complicated. It comes from this portion as well as this. So it's a combination of this. It turns out that, again, these two models are completely algebraically equivalent. And these equations, actually, the simple equations actually will show you how to derive one set of parameters with the other. And one thing to note here is that the growth term is a simple division. So to obtain this, the slope term is basically a simple division, and you divide by 1 minus the autoregressive parameter. And that also actually happens for, but the mean here is not as simple, it's more complicated. So at some point we kind of thought, well, perhaps this actually happens for all the covariates. And we fooled ourselves, and for about a month almost, we kind of thought that this is like just not an issue. Until we started seeing enough evidence that it is an issue. But anyway, so I worked through the quadratic growth model. So again, we have in the quadratic growth model, you have again the residual AR1 model. Basically, you have the quadratic trend, and then you have the autoregressive equation for the residual, and then you have the full AR1 model with a quadratic trend, where the equation has the quadratic trend within the autoregressive part of the model. And so it turns out that, again, these two models are algebraically equivalent, but the equations are not different. So you can obtain the parameters for the residual AR1 model through these equations using the parameters of the full AR1 model through these equations. And what you can see here is that the quadratic term now has this relationship that this coefficient satisfies this relationship that you can just obtain gamma 2 from beta 2 by just simply dividing by 1 minus the autoregressive parameter. But the relationship for the linear trend now changes. So it's no longer that simple, it's no longer this term, but it's something more complicated. So that's kind of an evidence that, obviously, things are more complicated than we thought. So we went back to this model and we try and see if it's really identified. So this is what I'm going to show you here. It's a little simulation where we're going to we're going to generate data from the joint model, and we're going to estimate it with the full model and also the residual model. And so again, this is, the covariate actually, and this is in a two-level framework. So we have the residual, we have the effect of the covariate is outside of the autoregressive equation, but it's also inside. So we have the two regression coefficients, and beta 1 is 0.3, beta 2 is 0.4. When we generate this covariate, of course, it's important to figure out how to generate the covariate. So we generate it from an AR1 process, and we vary the autoregressive coefficient for that generation process. So when you have Rx equals 0, the covariates are independent of each other. And as you approach, you can increase this Rx to, if your Rx converges to 1, then the covariate becomes a lot more like the time variable. So anyway, so we will generate data according to the full joint model, the joint model, and then we're going to analyze this with the residual AR and the full AR. And here are the results of the joint, analyzing the data with the joint model, and you can see that in all the cases, the parameter estimates are estimated very well, and the coverage is quite good. And so that what the conclusion here is that this model is well identified. And so for general covariate, time specific covariate, you can add the covariate in both places, inside the autoregressive equation and outside. So when we analyze the model with the residual AR, then we have just basically we estimate the model excluding this term, excluding that term. So there technically is no true value for beta 1. I sort of will say, well, we can maybe assume that the true value is 0.7, but there is no true value for that parameter. But the results clearly indicate, as you can see here in the phi parameter, is that the parameter estimates are biased, and it's depending on the actual parameters you use in the simulation, that bias can get in very bad. Basically, it just happened here that it looks a little bit small, but it's actually depending on these. The generating model, whether it's closer to the residual or the full AR model, you can get these biases to be, either big or small. So it's not that this bias is always looking small. So anyway, the beta coefficients, of course, is misestimated. So it's just all over the place essentially, and also the autoregressive parameter is misestimated as well. And the same thing happens when you do when you analyze the data with the full AR model, which is basically trying to put the covariate effect only in the autoregressive, so without this effect. And again, we have the same problem that there's no clear definition of what beta 2 would be. But if you assume that beta 2 should be just the sum of the two betas, you again clearly see that the parameter estimates can be the parameter estimates are biased, and also the autoregressive coefficient is also biased. So the conclusion of this little simulation is that there is, in general, for a general covariate, except when the covariate is the time variable or the time variable and the time variable squared, as in the quadratic model, or generally the general polynomial of the time variable. Except in that case, for all other residuals, the residual AR model and the full AR models are not a reparameterization of each other. And you can have this option of, you have this question of where to put the covariate. We are sort of arguing that, we're coming sort of new to this field, and so, personally, I don't care about tradition and, like what other people have been done in the last 50 years. I don't think that, this question of where to put the covariate should actually depend on what has been previously published in the literature. I think, the only thing that should decide this is the data itself. And so, and you can actually have, in general, it's very easy to test in which equation the covariate should be. You can put it in both equations, estimate it, and see which of the two parameters is significant. And actually, yesterday, Ben showed you an example where the DIC clearly indicated that the placement of the covariate was better in certain situations. It would be better to be within the autoregressive part of the model. One other thing to note here is that because I use the MIR1 model because it does have this flexibility of having the two equations with two separate residuals, and I can do this more easily where I can place the covariate in or outside of the autoregressive equation. But in the AR1 model, that is a problem because you don't have these two residuals, and so separating the two equations, it will be separating the two regressive parameters is difficult, and you have to create this residual and then fix it to 0. And this is basically the reason why we are started being interested in the residual DSEM model, is because this fixing of the residual is causing slow convergence, and it's to be able to estimate the residual AR1 model. The perfect framework is to actually use the residual DSEM framework model that I showed you, the general definition that I showed you earlier, which kind of extracts the structural equations separates the structural equations from the autoregressive part of the model. So anyway, the RDSEM model will absorb this complexity when it's available. That RDSEM framework is really where you want to estimate the residual AR1 model.